Alright everybody, so this video is the bridge between exponentials and logarithms. We're going to be talking about inverse functions. So remember, the definition of a function f of x, is a rule that takes inputs x and replaces them with outputs f of x. And you can see down in the lower left-hand corner we have a little picture of the function machine, and the function machine eats variables like x and then spits out f of x. And so we have a couple of examples of functions here. Here's one, f of x equals 3x minus 4. And when you see that, you can pick some values. And when you pick your values, all you do is you plug them in. Remember, the whole point of a function is every time you see x, you replace it with what you're plugging in, right? So if I was to write f of negative 2, instead of that, I could write 3 times negative 2 minus 4. And 3 times negative 2 is negative 6 minus 4 gives us negative 10. 3 times negative 1 minus 4. 3 times negative 1 is negative 3. Negative 3 minus 4 is negative 7. We have 3 times 0 minus 4, and that's negative 4. We have 3 times 1 minus 4, and that's negative 1. And we have 3 times 2 minus 4, which is 2. And now we have another example. Here is g of x is the square root of 8 minus x. And so again, we can pick some values. Let's do negative 1. Let's try 0. Let's try 4, 7, and 8. Those may seem random, but I want them to work nicely. So remember, again, every time you see an x, right, you're going to take your value and you're going to put it where every x is. And so what we get is the square root of 8 minus negative 1. 8 minus negative 1 is 9, so it's radical 9, which is 3. We get radical 8 minus 0, which is radical 8. That doesn't simplify. Radical 8 minus 4, which is radical 4, which is 2. Radical 8 minus 7, which is radical 1, which is 1. And radical 8 minus 8, which is radical 0, which is 0. So there are some values for our function g of x. So the domain of a function is the set of all allowable inputs. And the thing you should remember, basically, when I ask you, or anybody asks you, what's the domain of your function, if you can't plug it in, if the function sort of gets visibly ill if you try to plug it in, it's not in the domain. And so let's go back and look at our two functions. Here we have a polynomial, right? F is a polynomial. So all inputs are okay. And the way we write that is that the domain is all real numbers. Here, right, g of x is the square root. So the radicand, right, and remember, what's under the square root is called the radicand. So the radicand can't be negative. And so we take what's underneath, 8 minus x, and set it greater than or equal to 0. And if you solve, you see that that's x less than or equal to 8. And what you can see when we got to 8 was when we hit 0 for our answer. And if we put in any number bigger than 8, the radicand will be negative. And so this is the domain. There. Alright, so the domain is the set of allowable inputs. So let's go ahead and do a couple more quick domains. Here we have another polynomial. And what that means is that the domain is all real numbers. Here we have another one. G is the square root. So we need what's underneath to be greater than or equal to 0. So a graph is a collection of all points of the form x f of x for all x in the domain, right? So you think of a graph and you think of some sort of a drawing, right? There's a graph, and maybe since we're now doing trig, there's a graph, right? And these are graphs, and they're pictures, but what's more important is anytime you have a point on your graph, it satisfies that its coordinates have to be x comma f of x, or x comma g of x. And it's important that the values have to come from the domain, right? If something's not in the domain, it's not going to be on the graph. So here's 2x minus 1, and we sort of know how to do this. If we put a point at -1 and make a slope of 2, and we sort of draw our line going through these points, this is f of x, and that's f of x because we know how to graph a line. And since it's a polynomial, its domain is all real numbers. But look at any point that's on here. This is 1 comma f of 1. This is 0 comma f of 0. And if you come over here and you do f of 0 equals 2 times 0 minus 1, which is -1, this should be the same as 0, -1, and it definitely is. And f of 1 is 2 times 1 minus 1, which is 1, and so this should also be 1 comma 1, and it is. So you can see the relationship between what's in the y value and what the function tells you when you plug in the x value. So you always start at the x value and get the y value. G of x equals x squared minus 2. I'm going to go ahead and plot some points. You can verify that these work. And what we get is a parabola, g of x equals x squared minus 2. And so here is the point 2g of 2. 1, g of 1, 0, g of 0, and so on, -2, g of -2. So let's go ahead and just calculate a couple to make sure that this makes sense. G of -2 is -2 squared minus 2, which is 4 minus 2, which is 2. And so this should be -2 comma 2. And again, there's y equals 2, and so it is. And then let's go ahead and plug in 1. G of 1 is 1 squared minus 2, which is 1 minus 2, which is -1. And so that should be 1 comma -1. And again, that is. And so you can see how, again, there's a correspondence between how we label the points and the function, and that correspondence is always that the y value is what happens when you plug x in to the function, and you get the y value. So for inverses, we ask the question, what happens if we switch stuff around? Right? And so there's two things that we talked about. One's the graph and one's the actual function itself. And so what happens if we just switch all of the coordinates, right? If we take every x f of x and switch it to f of x x, and so if you saw a point like 1, -1, we could ask what happens if we make it -1, 1, and so on like that. And so the effect, right, changing xy, right, really we're asking change xy to yx, it's the same as reflecting over y equals x. So maybe we graph something like y equals 2x plus 1, and so the points that we get are 1, and then a slope of 2, and then we draw a line through them. And then here's a couple of points, 0, 1, and 1, 3. And remember, it's take 0, 1 and replace it with 1, 0, and take 1, 3 and replace it with 3, 1. Right, these are the reflections over the axis. If it's actually on y equals x, it stays where it is. And so when we connect all those, what we're going to get is this line. Right, and so if this top line here, let me grab another color. If this top line is f of x equals 2x plus 1, this bottom line is what we're going to call f inverse of x. And we'll figure out how to get an equation for that, but for now, just know that the effect of flipping over y equals x gives you the inverse function. So in terms of the functions, instead of just dealing with the graphs, because you're not always going to have a graph, and a graph is certainly not the most convenient way to do anything, how do you form the inverse? Right? Remember, what we want to do is we want, instead of taking in x and spitting out f of x, we want to do it backwards. And so the idea is that you want to eat f of x's and spit out x's. Right? And here's an equation that embodies that spirit. F inverse eats f of x and spits out x. And so how do you do that? Like, what's the practical application? Well, before we do that, well, here's the practical application. We'll come back to that in a second. So how do you find an inverse? Well, start by writing out the function, and instead of writing f of x, you can write y for this. And then switch every x and y. And what you're going to get when you do that is a new sort of function. And then when you solve for y, what you get at the end of solving for y is actually f inverse of x. So here's an example, f of x equals x squared. So remember, step 1 is write y equals x squared. Instead of writing f of x, you can write y. Step 2 is switch. So change every y and every x. And step 3 is solve for y equals radical x. Now, we're going to have to go backwards in time in a few seconds to talk about why I chose this, why it's not plus or minus x, and all sorts of things. There's a lot of problems here, but for now, this is good enough. When you graph the square root of x, it looks like this. And you should see, sort of, if I have y equals x and y equals x, up here in the first quadrant only, right, if you flip y equals x squared over y equals x, right, if you were to switch everything over this, what you would definitely get is the square root function. And if you flip the square root function over, right, like this, what you would definitely get is x squared. Right, so they definitely look like you have flipped them over y equals x. So let's go back in time. There's some things I skipped. One is that the inverse, right, so you're switching all of the x and y values. Remember, you're taking x, y, and you're switching it to yx. The x values that are okay is called the domain. The y values you can make is called the range. So the inverse function, if we're talking about the domain of the inverse function, we're now talking about y, and that came from the previous range of f of x. And the range of the inverse function, which is, here, came from the domain of f of x. So you can see that range and domain switch. If you know the range of the function, you know the domain of the inverse function. If you know the domain of the function, you know the range of the inverse function. So when is it okay, right? That's the question of domain. What can you plug in? Well, what you can plug in for f is what you can get for f inverse, and what you can plug in for f inverse is what you can get out of f. So let's look back here, right? The square function, the actual function that we're working with, can't make negative numbers. And so you should notice that the domain f inverse of x equals radical x can't take negatives. And the reason why it can't take negatives is because x squared can't make negatives. So what one can't take, the other can't make. So that's really important. So here's the problem alert. The function you start with might not be one-to-one. And if it's not one-to-one, the inverse, you might need to restrict it. And so let's look at what I did. When I made the inverse, when I solved, I could have written y equals plus or minus radical x. And if you square both sides, you get y squared equals x again, right? If you go backwards, you get the right equation. And so y equals radical x and y equals negative radical x work, but if you try to graph both at the same time, right, if you really, really try to do it, right, if this is the original function, and you just flip it, here is the inverse. There's x squared, here's radical x, there's negative radical x. Right? They're sort of divided across the x-axis. And this isn't a function. If you were to draw a vertical line, it would hit twice, and that's not a function. And so you have to choose. You either choose y equals radical x as the inverse, or y equals negative radical x as the inverse. And we made the choice for y equals radical x. So if, this is the most important thing about inverses, if two things are inverses, then when you do them back to back, you get back your input. See this? You get back your input. So, for example, if we do the square root of x squared, we should get x. And if we do the square root of x squared, we should get x. Now, it's important that this is only for the domains, right? It's only for the domains of the two functions. So the square root function can only take positives. So if you take the square root first and then square it, you'll definitely get back a positive number. And the square root is only going to, because of the domain restrictions, we're only going to allow positive squares, and we're going to get back positives. And I guess that's really it. So go ahead, play with the homework. It's a lot of stuff about inverses. And then we'll start talking about logarithms, which are the inverses of the exponential function. So do the homework. I'll see you in class.